Particles can be smeared out and act like waves. Things can be interconnected even over great distances. Time is smeared out. Everything is kind of different at that level. The boundary between this quantum world and the classical world, the Newtonian world in which we live, is unclear. It's called, some people call it the collapse of the wave function, because below that level, in the quantum world, things are governed by the quantum wave function. Above it, they're governed by Newtonian physics, classical, that we can understand. So this boundary is very unclear. And it was exemplified, the problem, for example, of superposition, of things being in multiple states at once. Quantum superposition means that things are superposed in two or more different places or states at the same time. So Erwin Schrodinger, in 1937, one of the pioneers of quantum theory, came up with a thought experiment to demonstrate how bizarre and seemingly ridiculous this situation was. He said, we know that something small like a photon or an electron could be in superposition. If we send a photon through a half-silvered mirror with a 50% probability that it will go through and a 50% probability that it will be reflected, quantum theory tells us that the photon will actually both go through and not go through. So if we have that photon, if it takes one path, say reflected, strike a vial of poison, and there's a cat inside a box. Schrodinger said that quantum theory would predict that since the photon both went through and did not go through, the poison would both be released and not be released, and the cat would be both dead and alive. In other words, the quantum superposition would be amplified to apply to the cat. And there was nothing in quantum theory or in physics whatsoever that would preclude that possibility. The only thing that seemed to occur would be that if quantum superposition was observed by a conscious observer, then it would collapse to either dead or alive, one or zero, one or the other. And so Schrodinger said, well, the cat is both dead and alive until someone opens the box and looks at it. And this is called Schrodinger's cat. It's a famous paradox. And to this day, it's still somewhat of a problem, although we don't think necessarily that you need a conscious observer to cause the collapse of the wave function, to cause the cat to choose one or the other. It may be that any interaction with the environment, any interaction with the outside world will cause the quantum system to reduce to one state or the other. But what about a system that remains isolated? What about a quantum superposition that remains isolated from the environment, from the outside world? There's nothing that tells us what will happen to it, and it can grow and stay in superposition. And this property of superposition, despite the fact that nobody really understands it very well, is used in quantum computers, which were first proposed in the 1980s and are now being built and developed very rapidly. The basic idea in quantum computing is that, well, in a classical computer, you have bits, right? Bit states, 1 or 0. And they interact, and you can compute, and of course, computers are great and do all kinds of things. Now, in a quantum computer, the information can be in quantum superposition, so that you can have, in addition to 1 or 0, you can have a quantum superposition of 1 and 0. These are called quantum bits or qubits. Okay. So the qubits in superposition can talk to each other by non-local entanglement. And while in this state, can do incredibly efficient computation. And in fact, Peter Shor in 1994 proved that mathematically that if you could build a quantum computer, they would be able to solve certain problems much, much faster than conventional computers. One of these problems would be factoring large numbers into their primes, something that's very difficult for classical computers. That problem, factoring large numbers into their primes, is the basis for nearly all cryptography, bank codes, military codes throughout the world. So when governments and industry realized this, people began pouring money into building a quantum computer. So that, because if somebody had it, all the codes would be obsolete. So the race was on. And now there are other applications too. But it seemed difficult at first because the problem with the quantum computer is these superpositions are very delicate. Any interaction with the outside world will disturb them, will cause them to decohere, to lose their coherence. And then several people came up with the idea that you could actually build quantum error correction. You can build into the system an algorithm that will detect decoherence before it destroys the quantum system and correct it. So that seemed to help things along. But even so, most quantum computers are being built at very low temperature to avoid thermal oscillations, which makes it unlikely at first glance to occur in the brain because the brain is fairly warm. Nonetheless, Roger, in his book, suggested that somehow the brain performed quantum computation, that there were superpositions going on, and that this could solve the problem of non-computability and free will. And he suggested, for example, that there could be a superposition of a nerve firing and not firing, that the nerve firings were the qubits or quantum bits. I read this, and I thought, boy, he's really onto something here. At a gut level, I think this quantum computing in the brain is a good idea, but I thought maybe the level of neurons firing and not firing might be too high a level. You know, maybe the microtubules that I've been studying for 20 years at the molecular level, at a much smaller level, were doing the type of quantum computation that he was looking for. So I contacted him, and we got together, and to make a long story short, we began working together to develop a model of how quantum computation could occur in the microtubules inside the neurons at a much smaller level, which would be much more conducive to quantum mechanisms, quantum computation. And microtubules seemed very well designed to be quantum computers. So that's what we did. And but yet people would still say, well, what about the hard problem? How are you going to explain experience? So let me go back to the Greeks for I forget which one, actually. It might have been Democritus, who said that atoms had elements of psychic mental value. The idea that there's something in nature that has the raw component of conscious experience. This developed into a philosophy called Panpsychism, where everything had consciousness, like this table had consciousness, every little thing had consciousness, which is not quite, which isn't really satisfying. And it evolved over the centuries and millennia, actually, into something called pan-experientialism or pan-protopsychism, if you will. And for example, a philosopher in the early 20th century, Alfred North Whitehead, came up with an idea that of pan-experientialism. Sequence of events, discrete events, occurring in a wider field of proto-conscious experience. Now, a philosopher named Abner Shimoni said that maybe Whitehead's occasions of experience were quantum state reductions, like in a quantum computer. Mm-hmm. But what could be the wider field of proto-conscious experience? Well, let's go back to what superposition really is. As I mentioned, quantum computers, which are being built today, even as we speak, in various forms. Successfully? Prototypes successfully, and they're making progress faster and faster. They're doing it with ion traps, with spin polarization, quantum cells, and even in silicon, with a certain way of constructing silicon. We don't have a quantum computer on desktops yet, but most people in the field are, after some pessimism, are now encouraged that they will be developed. Prototypes do exist, and you can solve certain problems with, I think, 8 qubits is the current limit. And because they're so fast, you don't need a lot of qubits, but it looks pretty good.
In order for that to work, don't you have to have a level of predictability? And how do you have predictability if you don't? You know what I'm saying? If you're saying that at that level, it's a Schrodinger's cat situation, right? I mean, you can't predict it. Then how is the computer? I mean,
right.
There has to be predictions for it to actually work, correct?
Right. Well, there's two answers to that. One is that they use massive parallelism. Because of the quantum superposition, you can be doing many computations, almost an infinite number of computations simultaneously, so that you can sort of average out any errors, any randomness.
Or answers, then. So basically,
no, the answers, because the answers settle into a interference pattern, and you query that, and that's what gives you the answer.
So there is some predictability.
Yes.
It's not completely unpredictable.
Correct. And the other answer to that is it depends on how the wave function collapses. Now, in quantum technology, there is randomness in the collapse, and they get around it by massive parallelism and redundancy. Mm-hmm. But in the brain, we think it's different, and that's the key point. It goes back to the idea of what exactly quantum superposition is. As I said, quantum computers use this idea of things being in two states at once without addressing the problem, well, how can things be in two states at once? Roger Penrose addressed that problem in his books, and his answer was that a particle can be in two places at the same time because reality itself separates.